using the addition rule for mutually exclusive events. Now, refresh the addition rule. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, because this is the overlap, right? Where we counted an item in A and in B. Well, we don't need anything twice, so we subtract the overlap, which means we're just left with one, right? That's the idea of subtracting the overlap. Well, when we have mutually exclusive events, that means there are no shared elements, meaning the probability of A and B is 0. So if we're subtracting 0, it's like this piece doesn't even exist, and we're just left with adding A and B. So let's go ahead and do that. There are 30 pencils in a box, 10 red, 12 blue, 4 green, and 4 orange. What is the probability of choosing a red or orange pencil? Are these mutually exclusive? Okay, so think about this. You're putting your hand inside this box. You're going to pick one pencil. To think about a shared, right, mutually exclusive, we're looking, do they share a common element? Well, if I'm only picking one pencil, I cannot pick red and orange, because that's the idea. Can we pick red and orange at the same time if I'm only picking one? And the answer is no. Red and orange would be a 0. So that means we are finding the probability of red plus the probability of orange, and that gives me the probability of red or orange. Okay, well, let's do this. The probability of red, well, there are 10 red out of 30 pencils, plus, what's the probability of orange? Well, there's 4 of those, so 4 out of 30, and that means I have 14 out of 30. Well, I'm not a big fan of non-reduced fractions. Those are both even, so 7 out of 15 would be my probability of choosing a red or orange pencil. And are these mutually exclusive? Yes, because they do not share a common element. Now, sometimes we will answer probability as a decimal. So 7/15 would be 0.467 to the nearest thousandths, in case you want to talk about decimals. Let's do one more. You randomly choose a card from a standard 52 card deck. What is the probability of choosing a 4 or a face card? Are these mutually exclusive? Okay, so thinking through a deck of cards, we have 4 suits. We have hearts, diamonds, spades, and clubs, and each one of these has ace, 2, 3, all the way up to 10, and then jack, queen, king. So there are 13 cards of every suit, which is how we get to 52, because 13 times 4 is 52. Now, the probability of choosing a 4. So we're looking at the probability of 4 or a face card. If you are not familiar, a face card is a jack, queen, or king, because they literally have faces on them. Like jack, queens, and kings. They're people, so they have faces. So a 4 would be a number, and then jacks, queens, kings. So these, yes, they are mutually exclusive, because 4s are not a face card. So they do not share any common elements. Okay, so now we're looking at the probability of choosing a 4 or that's not what I wanted, or the probability of choosing a face card. So how many 4s are there? Well, there's a 4 of hearts, 4 of diamonds, 4 of spades, 4 of clubs, so 4 out of 52. Face cards, there are 4 jacks, 4 queens, and 4 kings. So there are 12 total face cards. Because remember, there's 1 of each suit, so there's 4 jacks, 4 hearts, 4 diamonds, 4 spades, 4 clubs, and then the same for queens and kings. So when I add these together, I get 16 out of 52. And again, I can reduce. This is a 4 out of 13. And if I want to write that as a decimal, again, let's round to the nearest thousandths. I get 0.308. And that is the addition property or addition rule for mutually exclusive events. Just remember, mutually exclusive means the probability of A and B equals 0 because there are no shared elements. Thanks.